Okay, good afternoon, drone pilots. Today we'll be covering GPS and navigation. That includes GPS denied navigation. So GPS stands for Global Positioning System, and it consists of a constellation of satellites in medium Earth orbit above the Earth. Their distance is 20 kilometers above the Earth, so they are not in geosynchronous orbit. They orbit the Earth with a different period than the Earth than 24 hours. So a geosynchronous satellite orbits the Earth once a day, so it stays in the same place in the sky. But these satellites have a different orbital altitude, so they move through the sky. I will explain the principle of GPS, and then we'll get into the practice. So the principle is called triangulation. Consider satellite 1 and satellite 2 that where you know their position. This is known. And the satellites do know their positions and they broadcast their positions as part of their signal. So if you receive a signal from the satellite, it tells you exactly where it is. And you're an observer and you want to know, where am I? So the principle of triangulation is if you can somehow ascertain the distance to satellite 2 and the distance to satellite 1, then on a plane you can uniquely determine your location. Because if you know the distance to satellite 2 is D2, then you know your position is somewhere on a circle of radius D2. And similarly, if you know your position to satellite 1 is D1, then you know you're on a circle of radius D1 somewhere. So there's 2 points where those circles intersect, so you know you're at one of those 2 points. And that's the principle triangulation. Now, I learned this before GPS when I was in the Boy Scouts because we had paper maps and I would look at 2 different mountains and I would look at the angle to the mountain and draw with a compass on the map and I would get, it's slightly different principle, but where the 2 lines intersected, that's where I was on the map. So here, we're not using the angle to the satellite, we're using the distance to the satellite. Of course, you may be one of 2 points you don't know mathematically, but if one is out in outer space and one is on the surface of the Earth, then you should be fine. Now this works in 2D for circles. If you are in 3-dimensional universe, then the case works for spheres, and then circles you need 2 satellites. Spheres you need 3 satellites. So if there's another satellite somewhere else, let's say S3, satellite 3, you have to draw a sphere, which I'm not very good at doing. Even I can't get a circle done very well. So I have to turn to this is the best depiction that I have where there's 3 spheres, sphere 1, 2, and 3, and they intersect at 2 points A and B in 3-dimensional space. So that is the principle of GPS, and that's how it works. So how do we know the distance to the satellite? I'll give you a hint. The satellite is broadcasting its position and the time that it sent the broadcast. It's sending beacons. We'll talk about the protocol in a little bit, but it tells you where it is and what time it is every time it sends a beacon. So how can we determine the position, our distance to the satellite from that on the ground? What? Time difference. And how does that work? It takes time for the signal to move from the satellite to the observer. How much time does it take? Yes,
This should be distance divided by the speed of
speed of
light.
light. Exactly. So the light travels at the speed of light, but radio waves also travel at the speed of light. And if any of you ever have the privilege to take EECS 180A electromagnetics, by the end of the quarter, they'll describe Maxwell's equations and the wave equation, and that applies to all electromagnetic waves, light waves, infrared, ultraviolet, radio waves, all electromagnetic waves propagate at the speed of light. So the answer is the distance is the speed of light times the time. That's the travel time. T1 is the travel time. So if you turn around, the clock in the back says 12:39, but it's actually 12:36. So clocks are not perfect. So we have to deal with the imperfection of the clocks. And that was historically a big problem for GPS navigation. Because if your clock is off by a certain amount of time, your position will be off by a certain amount of time. So if we assume we have a perfect clock, here's a clock on the satellite, 12 o'clock, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 p.m. And let's say the satellite broadcasts the position at high noon, at exactly noon. And let's say the receiver has a clock, 12 o'clock, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the receiver measures the time. So the receiver, let's call this, well, I'm not going to do the math yet, but the receiver measures the time, and then he can determine the transit time. Because the clock says, I'm sending this beacon out at exactly noon, and the receiver receives it a little bit later, and he checks his clock when he received it. And based on that, you can find the distance D1, D2, D3 to the satellite. Each satellite broadcasts time that it sent the beacon. So the issue is that the clocks on the ground are not very good. And also for satellites, the clocks for a long time were not very good. So the satellite clock problem was solved by using laser clocks that are very stable. So the satellites now have good clocks, but the ground, we have bad clocks. I'm going to describe quantitatively what that means in a moment. So let's assume the satellite clock is perfect for the purpose of this discussion in the interest of time. But the background technology is laser clocks where there's a gas of atoms and there's an atomic transition between two quantum energy levels in the atoms. And that's the same for all atoms everywhere in the universe. And as you know, the Nobel Prize was given in physics this week for quantum phenomena. So quantum levels in atoms is important also in modern technology. So the energy level difference between between two states in some atoms is around 10 gigahertz. So you have a really nice 10 gigahertz source if you can phase lock an oscillator to the atomic energy level transition. And you can get nanosecond or better timing on that, which is good enough for GPS. It's much better than a nanosecond. The satellites, they do have lasers on board, but we only have 20 satellites, so we can afford 20 lasers. The issue is the ground clock. So typically on the ground, it's a quartz oscillator. Quartz vibrates mechanically, like any mechanical system, but any solid system will vibrate. But quartz converts a mechanical motion to a voltage. It's called the piezoelectric effect. So when the quartz vibrates, you get a voltage at the vibration frequency, which is typically, let's say 10 megahertz. And it's in all of the electronics that you use, computers, cell phones, laptops, everything. And it sets the clock frequency of your computer. If the quartz oscillates at 10 megahertz and your clock frequency is 300 megahertz, it'll use that as a reference and multiply by 30. So these are available and they're cheap, they're pennies, but the problem is their stability is about part per million. And they drift over on the day time scale. So this is why clocks are not perfect, free running clocks based on quartz, and they drift. And eventually they have to be synchronized to a better standard. So if, let's say it's a 1 megahertz quartz crystal, let's say it's drifting 1 part per million, then it drifts 1 hertz during the day. Or if you're trying to measure time, it drifts by 1 second during the day. So you may be off by a second a microsecond, no, that would be a second, yeah. If it drifted by 1 hertz in frequency domain, that would be a second in the time domain. So let's see, is that right? In a whole day. Let's do it like this. If you have 1 megahertz, then you get 10 to the 6 cycles per second. So in 1 second, you might get 10 to the 6 minus 1 cycles. So your error in 1 second is going to be a microsecond. So over the course of a day, it might add up to a second. But over 1 second, your drift might be a microsecond or more. So the speed of light is 3 × 10⁸ meters per second. And another good way of doing that is 1 foot per nanosecond. So if your clock is drifting by 1 nanosecond, you're going to have an error on that measurement of 1 foot. And clocks drift by microseconds or seconds. So the error on the measurement of D1, D2, and D3, it could be thousands of feet or more, which is not good enough for GPS. We want better spatial resolution. So that's the problem. And the solution to that is to add a 4th satellite. So the solution to that problem is to add a 4th satellite. So D1 is going to be C times T travel 1. But we don't know what T travel 1 is because our clocks aren't very good. We know it's T measured plus an error. That's the error in our ground-based clock. So we don't know that. This is unknown. Okay. D2 is C times T travel 2. This T measured 1 is C times T measured 1. T measured 2 plus the error. But it's the same error, because we're measuring all 4 satellites at the same time, roughly the same time. So that's where the math comes in. Similarly, the distance to satellite 3 is C times the actual travel time 3, which is C times the measured time 3 plus an error. And D4 is C times T travel 4. It's T times T measured 4 plus epsilon. So they're all the same error. So if we assume they're all the same error, then by adding a 4th satellite, we add another equation, and you need 4 equations for 4 unknowns. So when you do the triangulation, you have 4 equations, and you have 4 unknowns. Your unknowns are the x, y, z of the observer and the error of the clock. So if you have 4 satellites, you can determine the error, which you just throw away, but you can also determine x, y, and z. So that's shown in this series of equations more precisely. So the distance between the observer, which is the XYZ in gray, and satellite one, which is XYZ in red, is the Pythagorean theorem. It's the square root of x squared plus y squared plus z squared. And similarly for the distance to the other three satellites. And the time of travel is the speed of light times the actual time minus an error. So the error is unknown, but it's the same for all four measurements if you do them rapidly in succession. So now we have four equations and four unknowns. We have x, y, z, and b in gray, and we can solve those computationally. So that was a big insight that somebody had, I don't know who, that allowed very low quality clocks to be used and very inexpensive clocks to get very good precision on position. So that's the biggest problem that GPS had to make it massively adopted. In addition to having the RF circuitry, of course, which is, you all know, is also important. Okay, so why isn't it perfect then? What gives rise to the error in the GPS location? Why can't you find out exactly where you are at any point in time if this mathematics is true? What is missing? What are the sources of error? Can you think of some? I'm sure you can think of some. Throw them out and let's discuss them. Yes.
There could possibly still be like RF interference.
RF interference. That is possible. However, we do have error correction codes built in. And if you're not familiar with that, I can give you a short version. When you send an n-bit signal, it has to have a certain parity. It's either an even or an odd number of bits. And you always have a certain, you always transmit, let's say, where it's even. And if it comes out an odd, that means one of your bit has flipped. So you throw those out. So there are ways of mitigating RF interference with error correcting codes. What are some other sources of uncertainty in your position that people can think of? Yes,
The speed of light in a vacuum is not the same as the speed of light in that.
exactly. The speed of light in vacuum is not the same as speed of light in the atmosphere. So the distance equation the speed of light in air is the speed of light in vacuum divided by the index of refraction of air. In principle, you could measure that and calibrate it out. The problem is it varies with time because of the upper atmosphere chemical composition. So the ionosphere, if I have room, no, do I have room? No, okay. The upper atmosphere has charged particles in it because when the sun shines on the atmosphere, before it gets to the ground, it goes through air. And the initial sunlight is ionizing the atoms in the upper atmosphere. That means it's got enough energy that it knocks an electron off of the atom in the upper atmosphere. So that electron is free. Eventually it'll bind back to the atom, but then the next sunlight photon comes. So it's a balance. And then when you go to the other side of the earth, the sun's no longer shining. So now the ionic sphere has a different electron density, and that dramatically changes the index of refraction and speed of light. And it's not just day night, there's ionospheric weather, just like there was rain earlier this week, now it's sunny. So the ionosphere also has its own weather in the upper atmosphere, and it's turbulent. So that's the biggest cause of uncertainty with GPS, is that the speed of light changes with time in a way that cannot be predicted. So that gives rise to the biggest uncertainty in GPS. I'm sure you can think of a lot more. For example, you don't know exactly where the satellites are. There are still timing errors in the satellite clock, but the biggest uncertainty is the fact that speed of light is not constant, so you don't know. Okay. So you're welcome to dwell on all the errors if you want, but the speed of light is the biggest one. That is unsolved. Okay. We'll come back to the error in a moment. Let's talk a little bit about the RF communication. So the frequency of the satellite, there's L1, L2, and L5 frequencies for the US satellites. There are two streams of information. One is a spread spectrum over about 1 megahertz. It gives you 1 megabit per second. And then there's a slower one that's got about 50 bits per second of information. And this makes a fun exercise for the free transmission equation that we discussed earlier. Now, I would think that satellites, they would put out a kilowatt of power because it seems like it should be possible. But in practice, GPS satellites only put out about 50 watts of RF power. So that's plus 45 dBm in dBm units. And it's an interesting exercise to work out the signal and noise at the Earth. So the free loss is 180 dB. That's this equation here, 20 log base 10 of lambda over distance that we discussed in the radio theory section. So the received power is equal to plus 45 dBm minus 180 dB. So that means you're losing 10 to the 18 orders of magnitude in the power just from the fact that it's far away. So we can write that as minus 135 dBm if I have my math correctly. So if it's 40, it's minus 140. So let's just approximate it as plus 40 dBm, because what's 5 dBs between friends? So this will be minus 140 dBm, which is 10 to the minus 14 milliwatts. That's how it works. You take the 140 divided by 10, it's 10 to the minus that, which is 10 to the minus 17 watts. So 50 watts is transmitted from the satellite, 10 to the minus 17 watts is received by the antenna. So it's a very weak signal. Now the receiver sensitivity tells you the noise level of the receiver, and we discussed noise sum. And in order to spec that, you have to give a bandwidth, but implicit in there is the bandwidth of the GPS signal. So the receiver sensitivity is spec'd at minus 160 dBm, which is 10 to the minus 19 watts. So you still have 100x signal to noise, or 20 dB signal to noise. But the bit rate is slow. It's 50 bits per second. Okay. So you can do very long range communication. It's one-way communication, but you can't do it with high bit rate. So that's the GPS signal. There's an estimate of the GPS signal. So each satellite, like I mentioned, broadcasts its XYZ position to an accuracy of 1 meter, its own onboard clock to an accuracy of 1 nanosecond, and it's streamed at a baud rate of 50 bits per second. So every 6 seconds, each satellite gives you its position and time. And the message format is complex, just like UART and DSHOT. So we will not get into the detailed message that use binary phase shift keying. There's a whole entire course on Stanford that they posted on YouTube. They have almost 20 videos. The whole entire course about how GPS works. So if you're interested in the message protocol and the format, I would refer you to that course or the GPS documentation if you're so inclined. But this is meant for students rather than experts. Okay, so you have 4 satellites. You triangulate. You don't know the exact speed of light, and what you end up with is typically about 1 meter of accuracy because of the lack of the speed of light. it's better to have more than 4 satellites because you can triangulate better and you get better signal to noise. So generally you want as many satellites as you can, but 4 is the bare minimum. Without 4, you can't solve the math. If you have more than 4, you can average between all the different measurements and get a, roughly a square root of an improvement in your location. So 1 meter is a typical position accuracy. And that comes from the speed of light. Now, I'm going to come back to that in a moment, I think. But there is a possible degradation in that, which is shown by ArduPilot on your on-screen display, which is not a true measure of the error. The true measure of the error is you don't know. You don't know for a given lat lon how far away it is from reality. You only know statistically how far away it is from reality. But on a case-by-case basis, you have no way of knowing how far away it is from reality because you have no way of knowing the fluctuations in the speed of light at any given instant of time. There's no way to know that. Well, there is. We'll get to it in a minute. But with a standard GPS, there's not. So, however, if the satellites are distributed in an unfortunate constellation, for example, if they're all right on top of you, then it's very hard to triangulate. So you can consider the two-dimensional version. Let's say this is a two-dimensional version, and you have satellite 1 and satellite 2, and you know the distance to each. You have to find the intersection between 2 circles, and the circles are almost on top of each other. So the error is much bigger than if the satellites are far apart. So that specification can be calculated because you do know the satellites that are in view where they are. They're either above you or to the left or right because they're telling you where they are. So if they're all right above you, you have a degradation or dilution in precision. And that's called H-stop, horizontal dilution of precision, because they're all maybe right above you. That's unlikely, but it can happen if you get 4 lock and to be right above you, then you have H-stop greater than 1. And you'll be able to calculate that immediately from the location of those 4 satellites. So it's another reason why you want more. And there's a similar spec for the vertical dilution of precision beyond 1 meter. Well, beyond sigma, it's not really 1 meter. It's the statistical uncertainty that you would have if the satellites were all over the sky. And these are all displayed on ArduPilot, and usually ArduPilot and drone pilots want that less than 1 for them to fly, just as a quality control metric. And then one other thing to note is that the vertical is much worse than the horizontal because the satellites are above you, but they're all at about the same distance above you. So the Z error is much worse. So this is the horizontal statistical error, and this is the vertical statistical error. Okay. The US Global Positioning System has this website where they guarantee performance standards of the global positioning system. And it's usually 10 to 20 meters that they guarantee. But the manufacturers that manufacture the GPS receiver usually quote better performance. And as I mentioned, it's typically 1 meter horizontal, and it's typically twice as bad vertical. Okay, so this is your typical uncertainty in the horizontal position, lat lon, and this is your typical uncertainty in the vertical position. Now that's the 50% uncertainty. So that means that 50% of the time your instantaneous lat lon is within 1 meter of correct. And 50% of the time your instantaneous lat lon is not within 1 meter of correct. And that's why it's very hard for us to fly GPS lock in the drone cage, because the drone cage is 10 feet across, which is about 2 or 3 meters. So we could do an exercise if I was giving homework, but you can do the math and figure a Gaussian and fly your drone, put it right in the center of the cage, put it in GPS lock mode. Half the time it's going to crash into the net, and half the time it won't. And that happens. If you try it, you'll see half the time it crashes in the net, half the time it won't. So that's not really an ideal situation for flying, that half the time you crash. So that's another example of statistics. And the vertical is also difficult. So the vertical is worse because 3 meters, that's the height of the, so that means almost all the time your height is not known. So what is the solution for that in our class that you already have? Barometer, yeah. So you don't have to just rely on GPS. The barometer on the flight controller measures the altitude pressure, measures the pressure of the air, and that determines your relative altitude relative to takeoff. So the barometer is about 1/2 meter. So it's better than GPS. It's still not great, but it's much better. And by the way, it's relative. GPS is absolute. GPS is relative to the center of the earth. The barometer, when the weather changes, the atmospheric pressure at ground level changes. So every time pilots come into land at an airport, they always call the tower and say, what's the pressure at the tower? And they'll tell the pilot, and the pilot will dial it into their onboard avionics so that their altitude above the runway is known. And then if the weather changes, the pressure on the ground is going to change. So the calibration's wrong. So they always call right before they land. Do you have another point here in the front? Barometer? Yes, okay. All right. So in practice, don't try to get to fly GPS lock in our drone cage unless you're willing to have it crash. And it's not a horrible crash. It'll hit the net. I would recommend immediately disarming, and then it'll get caught in the net or fall to the ground. If it's caught in the net, just go get it. If it falls to the ground, hopefully it won't break because it's not falling that far. But you can fly in altitude hold mode in the drone cage if you want. So what I'm going to have you do is fly completely manually in the drone cage. I want you to control the throttle, and I want you to control the horizontal position. I want you to learn how to do it the old-fashioned way with no navigational aids. The only aid you have is auto leveling, and practice that. You don't have to be perfect at it, but please practice that. Because then when all these autonomous systems come in, you'll appreciate them all the more. Okay, so what is our GPS module? This is what it looks like. This is the antenna. Make sure it points at the sky. Don't point it at the ground. We found in the cabinet somebody had actually had it upside down. I don't know how it even worked. You don't get any lock when it's pointing upside down. And don't put anything over it. Like if you put a tinfoil hat over it, it won't work. Anything metal over it won't work. So this is the GPS antenna, and then internal is the circuitry. Actually, you notice there's a little battery here because it memorizes the constellation of the satellites to avoid having to look for them all again. So, and then it's got an LED here that tells you if it's got a lock. It's got an LED that transmits. So of course, like everything else, we have power, ground, and then we have a UART. We have a UART for TX and RX. So that just plugs into your flight controller, and you have a UART connection to the GPS. So that's your GPS. And we'll get to the other two pins in a moment. And here's the wiring. Good news, no soldering needed because it comes with this connector. And this is called a JST. You can also crimp those, believe it or not. And you can depin them and move them around, but that's really hard to crimp. And with this particular GPS model, it should have all these, and this is a DuPont. Now they're 1x1s. I recommend depinning the 1x1s and making a 1x6. Otherwise, every time you plug into the flight controller, the GPS in the flight controller, you're gonna have to figure out where each of 6 wires goes. And if you remove the GPS to do some other repair in your drone and you need to plug the GPS back in, you're gonna have to go back and look at the wiring diagram to figure out where every one of 6 wires goes. So depin the 1x1, put it in a 1x6, then it's much easier to plug it in each time and label it. And it's pretty amazing. I mean, it's a few dollars. You have one in your cell phone. It receives this teeny tiny signal from satellites all the way out in outer space and tells you exactly where you are within 1 meter. Okay, here's the specs, and I want to go over these in a little more detail just so you understand what all the specs are. So the chip is an M10. The company that makes most of the chips is U-Blocks, and M8 and M10 are their most recent versions of the GPS chips. The frequency is L1, which we discussed. They don't have L2 on here. However, the United States is no longer the only game in town. So GPS is USA, and it was developed by the Department of Defense in the United States. And it's an interesting story because the engineers that pitched it to the Navy before GPS was invented, they pitched it to the admirals of the US Navy. They said, we want $10 million to develop this global positioning system. And the Navy said, no, no way. That's ridiculous. It's never going to work. We're going to keep navigating with our ships by sextants. We're going to look at the stars. It's worked for thousands of years. We're not going to do it. So eventually, finally, somebody got convinced within the Navy to fund it, and the rest is history. So that's the US. Now, the US initially reserved the right to encrypt the signal. You mentioned radio frequency interference, but there's also encryption. And during times of war, they would encrypt it to degrade the performance. Unless you had the decryption key, you would maybe have 100 meters of spatial accuracy. So they would put in some random noise in there on purpose. And if you were in the military, you could get the decryption key and you could keep the 1 meter. And that was used, I think, historically during a few of the wars. I'm not sure. The Gulf War one, I don't remember exactly, but that was a policy of the US government when GPS was new. So as a result of that, in part, I'm assuming, and other reasons, the other countries in the world decided, well, we want our own. We don't want to rely on the US. So now there are 5 GPS systems from each superpower. US, China, EU, India, and who am I forgetting? Russia. So each one of these powers has their own GPS constellation. And they all broadcast at slightly different frequencies. So that's great for us because now we have lots of satellites we can use and we can pick and choose whichever one we want. And so the modern GPS receivers do use all of them. And that also makes the encryption obsolete because if the US encrypted all of its signals, then whoever wanted position could just use the other 4. So now there's no point in encrypting anymore. So you have all 5 of those in your GPS receiver. Okay, here's the sensitivity, which we discussed. Here's the horizontal accuracy. It's 1.5 CEP. That means 50% of the time it's within 1.5 meters of the truth. 50% of the time it's more than 1.5 meters away from the truth. And that's horizontal. They don't give you the vertical. So the vertical is typically 2 times worse. Okay, we have the speed accuracy, the angle, we have the time accuracy. You also get time from the clock. So I mentioned you can get the error. You actually can use that, and you can use the GPS receiver to have very accurate time. And a lot of people that are interested in having accurate time, you just put out a GPS receiver and they get a very accurate time compared to an off-the-shelf commercial clock. And you can pipe that in your computer and you can sync your computer time to GPS. It takes 27 seconds from a cold start to get locked. So it has to do some signal averaging and find where the satellites are. The baud rate is the communication rate in bits per second over the UART. And of course, it's UART, TTL. The protocol is NMEA or U-Blocks. We'll talk about that in the next slide. And then the update frequency can be changed. Now, there's firmware on there. We're not going to mess around with it. We're just gonna use the stock firmware, but it is possible to tell it through the interface, please change your update rate through the UART interface actually. So, but typically it's 1 hertz. So you get your GPS location once a second. The max height, the speed, the max gravitational acceleration, the voltage, it takes 50 milliamps of current. Here's the size, connector. So that's a JST 1.25 millimeter. That's the distance between the pins. There's also a JST 1.0 millimeter. So those are really hard to solder and to mess with. So they're pretty fragile. Be careful because they're pretty small. Okay, and then we have a LED that tells us when we have lock. So flashing when fixed, red when not fixed. And then the TX just says it's communication with the flight controller. So there's one other thing on here that's important for us drone pilots is the compass. So you can tell your XYZ position, but you don't have any idea what your orientation is, R, theta, and phi. And that's important for a drone pilot because you want to know which 2 propellers to spin up to go east or west. So if I spin up 2 propellers, I'm going to go east, west, north, or south, depending on which 2 propellers I spin up. But if I don't have any idea what the orientation of my drone is relative to north-south, then I don't know how to move north-south. So the drone needs to have information about the direction it's pointing. And for that, we use the Earth's magnetic field and a compass. So that's another chip that is also on your compass, on your GPS. Not all GPS modules have it. Most GPS modules do not have it. But drone pilots need it. So it can measure up to 8 Gauss. It has a noise level of 2 milligauss. It's a 12-bit ADC. So the bits are about 1 Gauss. And the Earth's magnetic field is 500 milligauss. So we're good to go there. It actually measures the magnetic field in X, Y, and Z. So that's also on your drone kit for us. And that's what pin 1 and pin 6 is, SCL and SDA. And you'll see that. So that's an I2C interface. And you'll see that on your drone, on the flight controller, it says SDL, SCA. We only have one I2C. So that's the wire up for your GPS. A little bit about the message format. So it's sending 2 possible formats. It's a bit stream. One of them is a ASCII bit stream. So you convert it to ASCII text, it's human readable. The other is a binary bit stream, which has to be converted if you know the format, and the format is public, but it's binary. So you have to parse the binary. That's more efficient. It was the ASCII came first, and it was invented by National Marine Electronics Association way before drones, when GPS was mostly used for ships. And it's ASCII, and then uBlocks is the company that came along that is the dominant market, has a dominant market share in GPS hardware, and they said, well, let's invent a binary format. So that's the binary format. So this is what a typical message would look like in ASCII. And if you hook up your GPS chip to a Raspberry Pi or even a computer, you can ask the computer to dump the messages to the terminal, and they're going to look like this. And you can see here, it's 48 degrees north, 11 degrees east. So it's human readable if you so desire, if it's NMEA format. And there's all these other fields. There's the number of satellites being tracked, the horizontal dilution of precision, the altitude, a checksum, time, and so on. Okay, so uBlocks is the same thing, it's just in binary. So if you dump the messages to the screen, you're just going to see a bunch of hexadecimal characters or bits. So you have to have a way to parse it. And it has similar information at time in milliseconds, lat, lon, altitude, so on. And if you have a Linux, there are a couple of programs called GPSD and GPSmon. They will parse those messages and just dump it to the screen, and they'll show you the lat lon of each satellite. On this one, you're seeing your lat lon. It's showing each satellite that it can view in orbit, and then it actually shows you the messages down here. It gives you the time and all the information you want. So in ArduPilot, you have to pick one of the UARTs. I picked you like everything else, there's many ways to do it. I suggest you do it the way everybody else does. Otherwise it gets confusing. So what I suggest is on the flight controller, there's an SDA, SCL, 5 volts and ground, and then there's a TX and an RX right next to it. So just put them all together. And I forgot what the number is, to be honest, but you can see on the flight controller, and it's in the parameter file, so you don't have to change it. But if you ever use a different UART, you have to tell ArduPilot and Mission Planner which UART it should be listening for the GPS signal. So we're using serial 3, which I guess is UART 3. Let me see. No. So, yeah, I just work here. Don't ask me, I just work here. So serial 3 is what it's called inside of ArduPilot, but UART 5 is what it's called on the board. So you have to plug the GPS on the board. It's labeled UART 5, TX5, RX5, but inside of the software, it's mapped to serial 3. So in serial 3, you make a GPS as the signal that it should, the protocol it should interpret, and then you're off and running. Okay, now that's GPS, but what about other ways of navigating? So the first one that I want to mention to you is the issue of the speed of light, and it's called RTK. So you're from the satellite to the robot, the distance is c times the time, but c is unknown. Speed of light is unknown. So that's what gives us our problems. So RTK is based on the following principle. Let's say you put a fixed antenna that's bolted to the ground that never moves, and it receives a signal from the satellite, and it's close to you relative to the size of the Earth. So it could actually in practice be 100 kilometers away, because the distance and the thing is, light propagates to you and to the antenna through air. So the speed of light at that particular instant in time is almost the same for both of those rays. If you're right next to it, it's exactly the same. But even if you're a few kilometers away, it's almost exactly the same. So you could use that to measure the relative distance between you and that fixed point mathematically. So the principle is that you don't know the absolute position in XYZ, but you know the speed of light. You know the time it took to get to the fixed point, and you know the time of the speed of light for that one is similar to the speed of light, almost identical, coming to you. And mathematically, then you can back out your location relative to the fixed point. Neither of you know where you are absolute, but both of you know where you are relative to each other very, very accurately. So that fixed point is called a reference station. And if you have a reference station, you need to be able to communicate. And typically that's done over the internet. So if you have an internet connection on your end and the reference station has an internet connection, you can communicate over the internet what you think the error is and what you think your positions are, and you can determine your absolute position, your relative position relative to the fixed reference station. So that can be good because you don't know exactly where you are, but you know where you are relative to the reference station. And with that, you can get 1 centimeter of accuracy. So the name of that is real-time kinematic. And that's what is used for surveying. Drone light shows use this because if you have a drone light show, the drones are less than a meter apart. So pure GPS doesn't work. And by the way, in drone light shows, they're doing waypoint missions. A drone light show is, we could even do one. A drone light show is just a whole bunch of EECS 195 drones flying waypoint missions. It's completely pre-programmed. You press the button and it goes. No pilot interaction until it lands. The whole thing is autonomous, which you're going to do. So if two of you do it next to each other, then we'll have a light show of two. If all 43 drones go up at once, we'll have a drone light show of 43. You just have to program them so they don't crash into each other. And please come talk to me if you want to do that, because we have an opportunity. But if we do it, we have to keep them more than a few meters apart. So if you use RTK, you can keep them 1 centimeter apart. Well, the resolution on their position is 1 centimeter. So if you keep them 10 centimeters apart, then you don't have any collisions. So would you guys like to have a guest lecture of a drone light show pilot? See if I can arrange it. See if I can arrange it. Okay. So Rover is another interesting example. So when you go out to the Arc, at night, there's a robot. There's a robot lawnmower. It's about the size of a car, but it's only about a foot high. And it mows the lawn, the entire athletic fields, all night long. And it uses RTK to fix the position because it doesn't want to go over to the edge of the lawn and hit the bush. It doesn't want to hit the sidewalk. So it's got RTK. That's another common example. And of course, it's supported by ArduPilot. There's a lot of RTK modules that you can get. The reason we don't do it in this class is that they're heavy and expensive. But if somebody wants to try it, they're getting them down now. This one says it's 21 grams, so that's light enough. We could handle that, right? We could handle easily another 100 or 150 grams. But it's $300. So it's a little bit out of the price range for you. But if anybody wants to, you can buy it and put it on your drone, and it should work. And ArduPilot will support it. So, or build your own. That would be a good student project. Okay. The remaining time, I want to discuss other navigation methods. And this not only applies to drone, it applies to all autonomous vehicles. So there's lots of other navigation methods that don't need GPS. The problem with GPS is you can't get it indoors. That's the biggest problem with GPS. Number one. So the satellite signal just does not propagate. And it'd be interesting exercise. Does anybody have one of the GPS apps that tells you how many satellites? There are some apps on your phone that'll tell you how many satellites. Let's see if I have it. Now, of course, your phone has more than just GPS. It's got Wi-Fi, but I don't. Let's see if I can GPS. Well, somebody can try it. There are apps that'll show you how many GPS satellites you're receiving at the moment. Well, your drone will. Okay, I'll tell you what. Forget the phone. I'll bring my drone in and I'll show you. Or you bring your drone in. You'll see how many satellites you have. It shows on the on-screen display. 0. So indoor navigation with GPS is difficult. Also, outdoor navigation with GPS is difficult if you have jamming. And somebody mentioned interference. So GPS is not terribly difficult to jam. So in Ukraine, there's a lot of GPS jamming. Israel, anywhere where there's a war, typically there's GPS jamming. So GPS becomes unreliable in the presence of jamming. But also indoors. So there are alternative methods of navigation. One is Lidar, which is you bounce a light wave off of an object and you measure how long it takes the light wave to get back. And by measuring that time difference, you know the distance to the object. So it's called Lidar. And this is an example Lidar that only weighs 5 grams that is possible to put on your drone. And we're going to buy one for you. I'll announce it in a moment. So this is Lidar. And here you go. TX, RX, VCC ground. So all you need to do is buy it, find a spare UART, plug it into the UART port, which you have one spare UART, and then tell ArduPilot the baud rate, the protocol, what kind of signal it uses, and which UART you chose. And then ArduPilot will integrate the LiDAR into its position estimate. So we haven't talked about feedback or state estimation yet. We'll do a theory lecture on that later. But ArduPilot is smart And it doesn't just rely on one sensor. It relies on many, many different sensors. And if the sensors disagree, it makes some intelligent decision which sensor it should trust. So that's called state estimation. It's a whole field of control theory. So have they covered that in any of the courses you people have taken? So there are theory courses where they cover state estimation for not just drones, but any system where you have noisy inputs and you want to know a good average intelligent guess of what the actual state of the system is. So ArduPilot has that in there. So it intelligently uses different sensors, and you can tell it to trust certain sensors more in the settings. So LiDAR is one. Another one is sonar. So you bounce sound off of something. And another one is radar. You bounce radio waves off of something. You send a pulse out, the pulse comes back, and you measure the time of flight. All these are time of flight based reflection sensors. And ArduPilot supports all of them. Here are a bunch of different components that are on the market that you can buy and put on your drone and plug into the UART and off you're running. And I'm going to buy one for you. We just ordered them on Wednesday and they should be here in a week or so. So I would like you guys to try it because we have the time, we have the money. So I think it's about $30 and I would like you to try putting it on your drone. So I'm going to explain to you this particular one. It's pretty tiny. And you can see right there, 5 volts ground TXRX. I've never used it on a drone. I've used it on an airplane because the LiDAR is short range. You can only go out to a few meters. It doesn't go very far, at least with these tiny little lasers. If you have a very powerful laser, it may go further. So this one, the max range is 2 meters. However, it gives you much better resolution on the altitude than the barometer. The barometer is ½ meter. LiDAR, I think, is a centimeter or less. So let's try LiDAR-based altitude hold in the drone cage and see if it works. So it's coming. So the LiDAR chip is, well, so let's take a look. Just like everything else, there's a microcontroller. It's an STM32. There's some firmware. Okay, we're not going to worry about the firmware. We got enough firmware we're doing. And let's just use the stock firmware. And then the LiDAR chip is, I think it's this one. And you just plug it onto your drone and you're good to go. It has to face down, of course, so the light wave can go down and come back up. So here's the ArduPilot manual for it. Here's the mate. It's made by the same company that makes your flight controller, Maytag, and it uses this LiDAR chip. So we're going to try. Now, the last sort of navigation method is visual reconstruction of three-dimensional scenery. Or you can also use LiDAR to reconstruct visual scenery. Or in principle, radar and sonar, although it's harder because of the wavelengths involved. But light, the wavelength is very short, so you don't worry about diffraction. And you can focus a beam very, very tightly of light waves. So you can point your laser beam in one direction and then move it by 1 degree and get a different reflection. So with a laser beam, if you could steer the laser beam, you can make a three-dimensional map of the reflection objects around you, which is a three-dimensional virtual representation of the environment. So there are LiDAR systems that do that. Has anyone ever driven in a Waymo? You have? What's it like? She has? In San Francisco or Los Angeles? San Francisco, okay. So there was no driver, right? So it's an autonomous vehicle, and on the top of it has a LiDAR that points the laser around and creates a three-dimensional map of the world, and then you get in it and it drives you to where you want to go. So that is a method of using LiDAR. However, it's a very, very big LiDAR system. It's the size of a desktop computer or bigger. So it's not drone available yet, at least not our small drones. But on bigger vehicles, you can use LiDAR to create a three-dimensional map of the world. You still have a range issue. So you have to have pretty powerful lasers to get 10 meters out. but it is in use in Waymo self-driving taxis. So we're going to get to that in a moment. That'll be the last part of the lecture, because so we'll get to that in a moment. But there's a prelude to that, which is called optical flow. So if you notice on here, there's a camera, and it's this chip, which is tiny, and it's a camera, but it's not just a camera. It's got a little bit of intelligence on it. And this principle of optical flow is very simple. You take a picture of the ground, and then if the drone drifts a little, you take a new picture, and you match the new picture to the old picture. And then you can figure out how far the drone has moved in XY. Pretty simple. It won't work if the ground is completely uniform. So if you're on a perfectly white ground with no features, it probably won't work. But if there's any feature like a little rock or a speck of dust that is visible on the camera, then you can basically just, in the computer, shift those two images until they overlap a certain distance, and that's how far the drone has moved. So that's called optical flow. And that's also on this Maytech chip, because it's pretty simple. And that's also supported by autopilot. So I'd like you people to try that also. And that will, if it works the way I hope, you'll be able to hover in the drone cage, because you'll have 1 centimeter XY control and you'll have 1 centimeter Z control. It'll be Lidar for the Z and optical flow for the XY, and you should be able to hover in the drone cage without doing any piloting at all. And here's a video of a drone pilot that has implemented that. And I'm very impressed with it. Once you start flying manually, you will be impressed too. Right now, it might seem pretty unimpressive, but try to fly in the drone cage. You can crash, that's fine. You built the drone, you know how to fix it. But it's a challenge for a brand new drone pilot to fly in manual mode in the drone cage and not crash. So I just want you to take off and land and make sure your drone flies. And then we'll start adding these features. But when you add this feature, it should be rock solid. So in my experience, that's a rock solid position hold, and there's no GPS. Okay, so please try it. I don't know where we're going to put that in the milestones, but we'll add it there. So the final frontier is image recognition. And this is what Tesla uses. So in principle, if you just have a few cameras and take pictures, you can create a three-dimensional model of the world. And this is how Tesla cars make models of the world and drive. So if you ever drive in a Tesla and you look at the flat panel in front, in some cases it'll show its model of the virtual world, its virtual model of the real world. It shows you a stop sign, a pedestrian, a car, etc. And that's all computational image processing of a series of cameras that are outside the car. Also, I would highly advise that you don't rob a bank if there are any Teslas parked in front, because there are cameras all over that thing. And so, yeah, so there's lots of cameras and very, very powerful computers that are tailor designed just for that process. And as we discussed with the battery, Tesla batteries can have 750 amps and 24 volts. So we have no problem with electricity on board a Tesla. And the weight isn't that big of an issue. So that is possible now to the degree that Tesla can do it with cameras in advanced computers. On drones, we're getting there. So I'm going to explain where drones are as of today. But eventually, if computers continue to get more powerful and lighter, then they will be used on smaller and smaller drones. So I can only tell you where we are now. I don't know how long it's going to take before our drone, well, I do know. I'm going to show you in a moment, because Qualcomm has developed a prototype of it. So, yeah, but let me go back one. Most of what ArduPilot supports is just time of flight distance to one reflector. So like LiDAR for your altitude. It doesn't support this three-dimensional image recognition, except for if you have two cameras. There are some double camera systems that do image recognition and develop three-dimensional models. And they're typically these Intel models. This one's $500, so we can't afford it, and it's too big for our drone. It probably would fit, but it's basically two cameras. With two cameras, you get stereo vision. So you get a crude image of the world around you. So that's supported by ArduPilot. But the ArduPilot is not there yet, and at some point, it becomes easier and more convenient to have the image processing not done on the flight controller, because the flight controller is pretty busy. It's got a lot to think about, and it only has 1 MB of flash. So give me a break. If you're going to do intense image processing, please buy another computer and put it on board, which we're doing. It's called an onboard computer. So we will do that in this class. We're going to use a Raspberry Pi Zero, and it will talk to the flight controller, but it will do all the thinking. The flight controller just does the core function, and then the onboard computer can do whatever you want. So one thing onboard computer can do is image processing. So in UAV Forge at UCI, there's a team, undergraduate team. Is anyone here members? It's mostly mechanical and aerospace engineering, and they build a much bigger drone, and they put a NVIDIA Jetson Nano on their drone that has a lot of computational power, and they have a couple cameras, and they can detect objects with artificial intelligence and navigate the drone using that. And they do that every year. There's a competition. Some years they have to rescue lost hikers. Some years they have to drop a rover at some location. So that's common on the very, very big drones. It won't quite fit on ours, but that is a project that they do every year. So there is a company that has done that called Modal AI, and this is a spin-off of Qualcomm. So Qualcomm invented a lot of the wireless communication technologies that's used in Wi-Fi and cell phones. And they also don't just do the theory, they do the wireless communication integrated circuits. And they also have digital integrated circuits. And their biggest market is the cell phone industry. So they have digital processors, and then they have analog radio integrated circuits, and they're integrated together. So it's a very big company with a big demand. So they spun off this small company called Modal AI, and that company developed a flight controller that's the same size and weight as your flight controller, but it's got not only everything your flight controller has, but it has an onboard Linux computer with 8 cores, 3 gigabytes, 3 gigahertz, 8 gigabytes of RAM, and a neural processing unit on board with 15 TOPS of AI performance, which is pretty good for an AI system. It only weighs 16 grams, and it doesn't dissipate a lot of power. So that company has a lot of resources, engineering resources, and they were able to develop this custom flight controller that can do both the flight controlling, which we normally do, plus full onboard Linux to do all the different things you want to do in Linux, OpenCV, ROS2, Docker, all the obstacle avoidance image processing that you want to do. So they've just released it, 16 grams, 8 core, and it's very expensive in prototype version. But they used my design. It's 2-cell lithium battery that's around 250 grams with 4-inch props. So your design is a very good design for prototyping. And it has about half-hour flight times. It's a really nice design. But I don't have all the resources Qualcomm has to develop an entire flight controller. So they did it, and they put it on there. And there's a demo here. There's 2 demos. One is, and there you go, there's a Radio Master transmitter and using Express LRS, which you all know very well now. So they have this image processing, and they can determine where the corners of the room are and become stable just with the cameras on a very small drone that only weighs about 300 grams. So that's one demo. And then there's another demo here where they actually, let's put it, yeah, I guess so. Sound. where they put it in a room and they develop a three-dimensional model of reality. So half an hour flight time, like I said, that's what you get with a lightweight, efficient design like you have. But there's also this onboard image processing, which they'll show in a moment. So here you go. So it creates this three-dimensional virtual map of the world, and then it can fly through obstacles and through loops and stuff. Okay. So that's that. Skip that. And the last technology on the market is the elephant in the room, DJI. So as I've mentioned before, DJI is kind of like the Apple of drones. They're not cheap, but it works out of the box, and they always integrate the latest and greatest technology. So the most recent version of DJI drones, their consumer, have Lidar, they have optical flow sensing, they have GPS. Let's see, what am I missing? They don't have radar, they don't have sonar, but still that's pretty good. And then they have the barometer. But they've gotten to the point now, and it's closed source. All their code is proprietary, just like Apple. So, but they've gotten to the point now where you can do return to home. Well, let me take a step back. So when you fly your drone, one of the things is check return to home. You go put in return to home mode. The drone will use the GPS and fly home and land. If there's a tree in the way, your drone will hit it. And you can have cameras that will see the tree and do simple obstacle avoidance. But DJI is really taking it to the next step by actually creating a three-dimensional map of the world. So they have two little cameras in the front here. I think there's two in the back. So they actually have not just the main camera for videography, they have these side cameras for doing image processing, just like the Tesla. So they have perfected that. And using that, it's actually possible to do non-GPS navigation, even with a consumer drone. Oh, let me go back. So the return to home, what that you do, if you lose GPS lock, your drone will not know what to do. Your return to home requires GPS lock. In fact, we should check that. We need to have a parameter that says if it loses lock, it just lands automatically where it is for safety reasons. Because who knows? There's 4 to 3 drones. Each one has 6 wires. One of those wires might break this semester. So let's make sure that if the solder job isn't working. Now you see why I'm so strict about all the soldering. But we need to make sure, I think it auto lands if the GPS is disconnected. Anyways, DJI, which I'll show in the last part of the video, the last part of the class, and we can do that at 2x, has developed it. It's on the Air 3S, which came out last year, and now the Mini 5 Pro, which came out this month, apparently also supports this. And so here's a video where the pilot is taking off in a garage. And you notice in the top right, there's 0 satellites. So there's absolutely no satellite signal here. So he takes off and manually flies it out. And all of a sudden he's got 20 satellites, he or she, and flies around. So let's see what happens when the pilot puts return to home mode. And I think one of these things up here says return to home. If anybody can translate for me, RTH. Because it's obviously done a trip. So tell me when it says RTH. Does that yellow thing mean RTH up here?
Yes.
GPS signal low. Okay. Yeah, there's no satellites now. But the drone has created an onboard memorized three-dimensional representation of the garage. and it's able to autonomously navigate back into the garage without any GPS signal. So there we go. Those are the current state of the art of navigation, GPS and GPS denied. Have fun flying in your drone in the drone cage with all the different technologies available to you.